Hi everyone, I'm Shun Fujita, and today I'm going to be presenting on the applicability of horizontal and vertical downward void fraction correlations for two-phase flow in a 90-degree elbow. So the table of contents, first of all, I'm going to start with the background, the objective, then moving on to the experimental setups, the correlations used, and then finishing off with results and conclusion. So to give a bit of a background, two-phase flow is basically the multi-phase flow between two phases simultaneously through a channel, and it has received a lot of attention in piping systems in nuclear, chemical, petroleum, and other industries because of its unstable nature due to numerous fluctuating hydrodynamic parameters. And this is important because it can cause sporadic forces, which can damage parts of the piping system in these industries. So, developing reliable models to predict two-phase flow is crucial for the safety of these industrial systems. So, some key terminology to know is first of all, void fraction. Void fraction is basically the amount of channel volume that's occupied by the gas phase. The flow regime is basically the flow structure of two-phase flow, and superficial velocity is just the velocity of a specific phase or fluid given a cross-sectional area. So the objective of my study was to compare existing drift flux correlations, which are basically two-phase flow models, to current data through a 90-degree elbow and analyze its applicability. So the reason why it's a 90-degree elbow is because there's not really much um, um, study conducted for two-phase flow through a 90-degree elbow. Instead, a lot of the past research has done on like one directional two-phase flow. So using current correlations and comparing their predictability with data that involves two-phase flow through a 90-degree elbow is possibly important to see if they can be applied to this as well. So the effects of an elbow on two-phase flow, basically it changes the direction. So it alters the structure, the void fraction distribution, the velocities, the phase velocities, and the pressure. And there's a lot more hydrodynamic parameters, but these are the most important ones. And so the flow regime, as I mentioned, is the flow structure. So depending on the speed of the gas superficial velocity and the liquid superficial velocity, the flow structure can change. So for dispersible flow is when gas velocity is very low, and when it's an annular flow or when it's annular flow, the gas flow is very fast. So the gas superficial gas velocity is really fast. So the correlations that were used are called drift flux correlations, and basically they are constitutive models to predict the void fraction based on relative motion between phases, and it includes two terms that are important, which is the distribution parameter and the void fraction weighted mean drift velocity, denoted by double brackets VJG, and distribution parameters denoted by C0. And so um, the distribution parameter describes the influence of the distribution of void fraction and the phase velocity of the void fraction, and the local drift velocity is given by this equation at the bottom, average over void fraction. So the correlations I used were Sam and Hibiki for the horizontal void fraction calculation, and Dong and Hibiki in 2021 for vertical downward void fraction calculation. And as you can see, these are very recent correlations, and they're developed on large amounts of data that are conducted previously by a large number of researchers. So pretty much the derivation of this, so basically these distribution parameter, void fraction weighted mean drift velocity, and the void fraction weighted mean gas velocity are defined in equations 1, 2, 3 respectively. And the double brackets just means that it's void fraction weighted mean quantity, and a single bracket is area average quantity. And so the one-dimensional drift flux model can be obtained in equation 4, and just rearranging that for the void fraction gives us equation 5. So the first drift flux correlation for horizontal void calculation was taken from Rasam and Hibiki, as I mentioned, and basically these are the equations for it. So there's different bounds um, for the situations that they could be used for. And so these are all the formulas you need to calculate the void fraction or the distribution parameter, which can be used in the one-dimensional drift flux model to calculate the void fraction. And so since it's a horizontal flow, so the gravitational acceleration is perpendicular to phase flow, the local drift velocity should be 0. And so the double brackets Vg is equal to 0 meters per second. This is assumed and the term is neglected. So this results in our following equation. Void fraction is equal to superficial gas velocity, or void averaged area average superficial gas velocity over distribution parameter times the area average superficial velocity. So moving on to the vertical downward calculation. So this was Dong and Hibiki's 2021's correlation. And so this was based on a lot more data compared to the first one. And it's used for vertical pipes. So, and these are the equations. So again, the bounds, there are bounds that these equations should be used for. And so, since the gravitational acceleration is not parallel, this means we cannot neglect the term that we did in the other one. And so it just gives us our original one-dimensional drift flux flow to calculate the void fraction. So the experimental setups for experiment 1, this is the experiment that I utilized the horizontal void fraction calculation. And so experimental 2 is the vertical downward flow. So for experiment 1, the two-phase flow goes up through the pipe and to the right, while in experiment 2, the two-phase flow goes from the right and down. So for experiment 1, some important points to note is just that it's conducting an adiabatic air-water two-phase flow in room temperature and atmospheric pressure. And these are some important points to know down below. So for experiment 2, again, this is conducted in room temperature and atmospheric pressures. And the pipes are made of PVC and acrylic pipes. And instead of flowing up here, since this is experiment 2, the water goes up here and it flows downward like this. So an important component of the experimental setups is the impedance probe, which is basically used to measure void fraction, and it consists of a pair of electrodes and electronic circuit, and basically the impedance measurement taken from the impedance probe is converted into a dimensionless voltage signal, which is then calibrated to make it into a void fraction. And because the electrical conductivity changes for air and water, this impedance probe can be utilized to calculate void fraction. And so there's two main types that are used. One was arch type, the vertical, for vertical calculation, and ring type for horizontal calculation. So the results were basically assessed using three methods. First, plotting calculated various experimental values, then visualizing the flow regime and identifying patterns of error, and trying to find out what the cause for error was. So here, this is basically just a void fraction calculation for this experimental graph on the right. And so the black line just symbolizes that it's 100%. So it's proportional, directly proportional. And so as you can see, the data points are within 20% mostly, with a bit of more error on the void fractions around 0.7, 0.8. So the average percent error is 28.74. Moving on, visualizing this data in the flow regime, pretty much the predictability deteriorates in bubbly elongated flow. As you can see here, it's very dark. And so dark values means a higher percentage error, while a lighter percentage error or lighter color depicts a smaller percent error. And so predictability generally improves in slug flow, but deteriorates again near the transition to annular flow on this to the right here. And void fraction data is generally more unstable in bubbly and elongated flow due from observation. And so to analyze the error, there's no really a clear relationship between the superficial gas velocity and error, but it does improve after the superficial liquid velocity reaches 0.610 meters per second, but after that, it pretty much stagnates. And so here is some visualized data of the void fraction that was calculated um, or observed. And so there's not really a much bigger difference other than with bubbly flow, which had a percent error of more than 30%. It's kind of unstable compared to the other two-phase flow void fractions. And so for vertical downward void fraction, again, this is the graph of calculation versus experimental. This time, it generally underestimates the void fraction, and it has a larger percent error for void fraction below like 0.7, 0.8. And so the average percent error is 33.66%. But the predictability improves significantly after like 0.8-ish void fraction. So again, this is compared with the flow regime map by Lokanathan in 2018. And the predictability is very unreliable in churn bubbly, cap bubbly, slug, and churn turbulent. As you can see, it's a much more clear relationship here, and it significantly improves in the annular dispersed flow. So here again, visualize data of the void fraction. For points with 50% error or more, you could see there's a very large fluctuation in void fraction. So the elbow probably kind of caused the two-phase flow to build up the gas in slug and cap bubbly flow. So this is probably a large reason why there's a large percent error. And so one of the considerations that I did was the kinematic shockwave, which represents a abrupt transition from bubbly to annular flow regime within the text section. But there's not really much evidence to support it because there's no data point within this kinematic shockwave. And so this was kind of an interesting thing to see, but we didn't have any data, so nothing can be concluded. So the error analysis, so basically there's not really a clear relationship between the percent error and this superficial gas velocity shown by this large dispersion of points here, the black points here. But the void fraction data shows very clear relationship between the percent error and superficial gas velocity depicted by this like clear inverse relationship. As superficial gas velocity increases, the percent error decreases. But void fraction data shows very unstable fluctuation at test conditions with lower superficial gas velocities, especially in slug flow. So a few conclusions can be made from my study, and this is based on a small sample, so we can't really make huge assumptions, but the correlation by Rassam and Hibiki 2018 shows decent overall predictability for horizontal two-phase flow involving a 90-degree elbow, but seems to be inconsistent for bubbly elongated bubbly flow and slug flow. And the correlation by Dong and Hibiki for vertical downward calculation was relatively reliable for void fraction calculation and annular flow, involving a 90-degree elbow, but unreliable for bubbly cap, bubbly slug, and churn turbulent flow. And so from the error data, the elbow seems to disrupt bubbly and elongated bubbly flow, and possibly the transition from the annular and horizontal two-phase flow. But major differences in void fraction behavior was not observed. And also, the 90-degree elbow seems to disrupt two-phase flow with lower superficial gas velocities in vertical downward flow, especially, which is potentially, a large reason for the error that was observed. So thank you for watching, and I hope you guys understand the presentation, and thank you again.